So let's see. So we're talking about zeros and everything. So what we haven't talked about yet is what we call the remainder theorem. Okay, and I'll show you kind of how that works. We went through, I guess, synthetic division mostly and kind of got the idea with that. So what a remainder theorem basically is if you have a function, we're just dealing with polynomial functions. If you want to evaluate the function, or like in this case, if you wanted to find what f of 1/2 is, there's two ways to do it. So I'm going to show you two ways to do this. I'm going to have you just kind of write down both ways you do this. First of all, let's just do the way we're used to doing. Let's just plug it in, and let me show you what happens. This is on page 2, okay? So we're going to do it this way to start with. So basically, everywhere I see an x, I'm going to put in a 1/2, like that. And then I've got plus 16 times 1/2 squared, and minus 8 times 1/2, like that. So you want to go ahead and get that written down. Then we're going to work it out this way, and then I'll show you what the remainder theorem is, and it's an alternative to doing what we're going to do by hand anyway, okay? All right, so we'll just work out some of the arithmetic. If you take a 1/2 to the 3rd power, that's an 1/8. Multiply a 1/2 out 3 times, you get an 1/8. Okay, then we have 16, a 1/2 squared, a 1/2 times a 1/2 is a 4th. And then we have 8 times 1/2, like this. This one actually kind of works out kind of nice. It looks like everything cancels out when you do this then. Okay, so what you would have is, this would be, you can do this all in your head. That's negative 8 over 8. That's 16 over 4. Minus 8 over 2. So that is negative 1 plus 4 minus 4. So that looks like that's equal to negative 1. So that's what f of 1/2 is. That's the standard way that we've learned how to do that, right? Just plugging in, working that out and everything. So what you would find on this, I think did I put this graph on your handout? I don't remember. Is this graph? I tried to put some graphs on here so we can kind of save a little bit of time. So what we have is this point right here. That point right there is the point 1/2, negative 1, like that. All right, so what we're going to do is we're going to do the remainder theorem. The remainder theorem is a different way of doing this. What you do is you can do synthetic division and get the function value that way. So let's do this. We're going to go ahead and set up 1/2, and then we're going to do synthetic division like we were doing last time, okay? Make sure that everything is, that you have a placeholder for everything. So we have an x the 3rd, an x the 2nd, an x the 1st, but we don't have a constant term. So when you do synthetic division, you have the negative 8, the 16, the negative 8, but you do have to have a 0 there because there's no constant term. So make sure if something's missing on synthetic division that you have a placeholder, okay? All right, now we're going to do synthetic division. So I'll review how we did this. And students usually don't have any problem with this. So the first thing you do is bring down the negative 8. Then it's just a matter of multiplying. So you're going to take 1/2 times negative 8 is negative 4. 16 minus 4 is 12. Then you do 1/2 times 12 is 6. Add the column, that's negative 2. 1/2 times negative 2 is negative 1. So we have that. All right, so what happened? I got negative 1. I got the function value, didn't I? Okay. And that's what happens on this basically is the remainder is negative 1. That means that's what the function value is. Okay, that's what the remainder theorem is. So basically what's going to happen is if you're doing the remainder theorem, you don't have to do this. Okay, you just do the synthetic division. And to me, synthetic division is faster than that is. What do you think? Okay. Generally, you'll be able to do synthetic division pretty quickly. And of course, you can check on your calculator. You can graph it, you could trace it a 1/2, and you can see that that function value is negative 1 anyway. Okay? So anybody have a question about what I just did? Okay, all right, that's what remainder theorem is. We're going to look at a couple of these, and the next one we're just going to do remainder theorem. We're not going to evaluate it. So what you want to do with this is you're finding f of negative 2, so you want to go ahead and get everything set up in your synthetic division. Okay, there's no missing terms. We have a x to the 3rd, so we use 1. We have negative 4, 3, and we have 5. So unlike the last problem, nothing's missing. Okay, All right, so what we do is just go through the synthetic division, and you can do this pretty quickly once you catch on. So again, you always bring down the 1, then you multiply. Negative 2 times 1 is negative 2. Add the column, that's negative 6. Multiply, negative 2 times negative 6 is 12. Add the column, that's 15. And then negative 2 times 15 is negative 30. So that would end up giving negative 25. Does everybody understand what I'm doing on the synthetic division? Okay, all right, that's pretty easy to do. It's the same process. Now your remainder is negative 25, so that means the function value is negative 25. All right, so the remainder, whenever you divide a polynomial by a number, that remainder turns out to be the y value when you divide by that. Okay, and if you look at this graph that I gave you, I even have the number on here. You have the point negative 2, negative 25. That's what we did. So you can tell you've done that correctly by just tracing out that value on a graphing calculator. Okay? So that's all the remainder theorem is. Does that make sense to everybody? Okay? Okay? So you can bypass just plugging the number in. You just do synthetic division to quickly evaluate your function. To me, that's usually a little bit simpler way of doing that. Okay, next thing that we're going to look at is the factor theorem, which is actually just an extension of the remainder theorem. And what we can do on this is we can tell if something's a factor or not by doing synthetic division. So first of all, the factors are always x minus a number. Okay, so if you had something like x minus 2, that's the kind of factor we're looking at. Or if you had x plus 2, that's another form of a factor like that. So basically what you do on this is you divide synthetically, and if it turns out to be 0, then it is a factor. Okay, so we use synthetic division sometimes to factor polynomials, and that's one of the things we're going to do. Okay, so here's what we do on this then. We're going to see if x minus 1 is a factor of this polynomial. So what you need to do is just do synthetic division. Okay, and it goes like this. There's no missing terms, so you would just put in the 1, negative 10, 27, and then negative 18 like that. And then you want to make sure you don't get this backwards. I mean, just always take the factor and set it to 0. So what's x in your head? X is 1, right? So don't get that backwards, so put in 1. If that was x plus 1, then it would be negative 1. So be sure that you use the right number there. Okay, just think of taking that factor and setting it equal to 0, and that'll tell you what to use there. Okay, all right, so now what we do is we just do our synthetic division. So you want to go ahead and do that. You can do that pretty quickly. You just want to see if the remainder is 0 or not. So bring down the 1. 1 times 1 is 1. Add the column, negative 9. Multiply, that's negative 9. Add the column, that's 18. 1 times 18 is 18, so we got 0. Okay, so is the answer yes or no? Yes. Yes, it's a factor, okay? So what we're going to learn how to do a little bit later in this section is how to factor. So one other thing I want you to write down on this is this, when you end up with this, the power goes down 1. So if it starts 3 and you divide, it's going to go to the second power. So this result would really be x squared minus 9x plus 18. So what you would have, and we'll work on this a little bit later in the section, is since it is a factor, x minus 1 times x squared minus 9x plus 18 is the factored form of that. And you may be able to factor that further. Okay, I'm not going to take it further on that. That's not the point of the problem. So what I wanted to show you graphically on this is basically when x is equal to 1, you have a point 1, 0. And again, that remainder is going to end up being the function value of that. And since it's intercepting on the x-axis, it's a factor. Okay, that's why. So you can tell visually that that's a factor by how that crosses the x-axis like that. Okay, at least at this stage. Okay, all right. So let's do the next one. I'm just going to do a couple of examples of these because they're all pretty straightforward to do. And this one, no missing terms. So we have 1, negative 10, 14, and 80. Now, what do I divide by? 5 or negative 5? Negative 5. Okay, make sure that you do that right. Yeah, again, you're just thinking x plus 5 equals 0, therefore x equals negative 5. So be sure that you divide by the right number. Okay? All right, so let's see what happens. Bring down the 1, multiply, that's negative 5. Add the column, that's negative 15. Multiply, that's 75. I have a feeling it's a no. What do you think? When you get to this point, you can stop, by the way. I mean, you don't have to finish that. I'm just going to say it isn't going to be a remainder of 0. Okay, so you don't have to finish out the details once you see that it isn't going to be a remainder of 0. And what will happen on this one, if you look at the graph that I gave you at 1, 2, 3, 4, negative 5 right here, can you guys see those numbers on your handout? It's like when x is negative 5, y is negative 365. Okay, so it's clearly not a factor because it's not equal to 0. That's the difference between the two. Okay, so that's what remainder and factor theorem are. They're basically pretty simple to do. We use the factor theorem to find all the zeros of a polynomial. That's what we're going to be working on today in class, is finding zeros of polynomials. The next section, 3.3, is the same thing, except it's got complex numbers. Okay, any questions so far? Okay, all right. Okay, so now what we're going to do is this kind of method here. I just want you to know how to create a list of possible rational zeros, and we're kind of bypass this some in practice when we're finding zeros. So basically what happens on this is a zero of a polynomial just causes the function to be 0. That's what we call it, a 0. Now in this section we're only looking with real numbers. In the next section we look at complex numbers. Okay, a real 0 is an x-intercept. Okay, so like on the last problem, for instance, if you go to example 4 on the last page, 1 is a 0. Okay, the x equals 1 caused y to be 0. All right, that's the idea. Okay, so what we're going to do is we're going to create this list, and this is just something I want you to know how to do. So P is always the factors of the number in front of the highest power. Okay, the factors of 1 are 1. The only number that divides into 1 is 1, so we say 1, but it could also be negative. So when you're doing these lists, what you want to have is both plus and minuses. Okay, Q is the other number, like that. Okay, so it goes like that. And what you would have on that then is hold on, I did that backwards. Okay, it goes like this. Sometimes I do that. So this is P, like that. That's P, and that's Q. Yeah, so P is the second thing. Q is the first thing. That's how that goes. All right, so let's start with P then. P is all the factors of 24. Now, there's a bunch of numbers that go into 24. So, and I always do my list like this, kind of go outside in. So 1 and 24 multiply together. You also got 2 and 12. Then you've got 3 and 8. And then you've got 4 and 6. So if you kind of do outside in, then that's a good way to keep track of all that stuff. Okay, and then they're all plus minus. So you got to put the little plus minus on every single one of those, because it's possible that your factors could be negative in this case. So you have that. Okay, all right, then Q is just all the factors of 1. So that would be plus minus 1. So P is the constant term. Q is what we call the leading coefficient. Okay? So now what you do is you do P over Q. So what you're doing is you're just creating ratios. So you're just going like 1 over 1, 2 over 1, 3 over 1, and so forth. So if you put all those things over 1, then the P over Q list just becomes the P list. So if you want to, you can just put, I don't mind if you guys do it this way. My math lab, they're going to want to put the plus or minus on every single thing. But you could go plus minus, and you could go 1, 2, 3, 4, 6, 8, 12, and 24. But you just got to realize that they can either be plus or minus. Okay? So what that means is this. All right? It means that, like if you were graphing this polynomial, okay, it's possible that some of the real zeros could come from this list. They don't have to, though. So I want you to notice on this that, notice that -2 is a 0. So that's in your list, right? Okay, another one I see in here is +2. That's also in your list. And then also 3 is. Now, they don't have to be in the list. It turns out that the P over Q doesn't have to be the zeros. Now, like when I was in college algebra, which was like about 1982, we didn't have graphing calculators, so what we had to do was we had to just sort of pick a number, synthetically divide it until we got a remainder of 0. That's how we found a 0. What we're going to do mostly is use our graphing calculator to find the first 0 and then find the rest of them with synthetic division. That's the idea. Okay? All right. So let's look at this second one then. Again, P is going to be all of the factors of 12. Okay, so that would just be 1 and 12, 2 and 6, and let's see, 3 and 4, and that's it. Okay, and then just have your plus minus on each one of those things, or you can do that shortcut if you want to like that. Okay, and P in this particular, or Q, is the number in front of x to the third, so that's going to be plus minus 1. So this works out the same way as the last problem. When you formulate the ratio, you'd have 1 over 1, 2 over 1, 3 over 1, 4 over 1. Well, you don't need to put it over 1, so the list would just be plus minus 1, 2, 3, 4, 6, and 12. Okay, there will be situations where Q might be some other number other than 1, and you have to formulate all those ratios like that. Okay, so what this means is, and what I did on your handout is I went ahead and graphed this polynomial, and notice that the 0 on this, it looks like 1, 2, 3, 4, it looks like it's 4 point something, right? So notice that's not in the list. So the thing is, the P over Q, they don't have to be zeros, but they are possible rational zeros. And this number right here where it crosses is likely to be some irrational number, like it's got decimals that repeat and stuff like that. So that's what your list is of giving potential rational zeros. Does that make sense what I did? Okay, all right. Only thing I really want you to know how to do with this is just how to make that list. We're going to bypass using this sum when we're doing the zeros in the rest of this section. Okay, so the next page we're going to go through, this just kind of is an outline of the steps that you can go through to find zeros. So I'm going to be going through that on the next page, and we'll do several examples on this then. Okay, so this is kind of what we're trying to do in this section. We're applying the factor theorem and the remainder theorem really to do this. So what we're going to do is I give you a polynomial, you're going to find all the rational zeros. Okay, now we're not going to do the P over Q list. What I would recommend you do on your homework is just use your graphing calculator to find a 0. Okay, so I went ahead and graphed this. So it already looks to me like you would have -2, 2, and 3. That's probably the answer. Okay, but we're going to do it algebraically. So what you want to do is just pick a 0. Okay, you're generally going to have something you can tell from your graphing calculator. So let's take like 2 for instance. Okay, so let's start with 2. So what we're going to do is we're going to synthetically divide the 2 into the polynomial. So that polynomial is 1, -5, 7, and -24, like that. Okay, now we should get a remainder of 0 when we synthetically divide this. So here's what we're going to do. All right, go ahead and do your synthetic division and see if you don't get a remainder of 0. Okay, so I'm going to bring down the 1. 2 times 1 is 2. Add the column, that's -3. Multiply, that's -6. Add, that's 1. What? No, did I miss something? That doesn't look like a 0 to me. Okay, I may have put the wrong thing in my graphing calculator possibly, because I didn't put anything wrong in there. What you guys want to probably do on this is, that's probably what I did when I was putting that together. I'm going to put this in the graphing calculator. You should go ahead and put this in the graphing calculator. And this is kind of what I'd want you to do on your homework anyway, is just find, you know, your first zero graphically. So I'm going to put that in and see if I did something wrong on this. I think that's what I did. And then you can just do that in a standard window. So you can go zoom 6. And let's see. It's cubic. Yeah, I did something wrong on that one. And I have a feeling that this problem is something that we couldn't do with synthetic division. That's what it looks like. I must have put the wrong problem in on that or something. Okay? Doesn't matter because we'll have plenty of other examples. So this one, actually, you would have to use technology. Okay? You couldn't do it any other way, and we'll get to that in a little bit. I obviously typed the wrong thing out on that one. I wonder if I meant to do this one, x cubed minus 5x squared. Well, that doesn't make any sense. And I just had the wrong thing typed out, I guess is what I did. That's okay. All right. So let's just forget about that problem. All right. Just forget it. Now that one, again, if you look at the graphing calculator, there's your 0. And we'll get to a point here in a little bit of how you have to use your technology to find that. Okay, that was not the intention on that problem. Okay, let's look at the next one. Hopefully this one's okay. So I went ahead and did the graph. So it looks to me like you have a 0 at 2, and it looks like you have a 0 at -1. Okay, now this is a 4th power, so you got to do something a little bit different on this. So let me see if I got this one typed out correctly. I hope so. Okay, so let's start with the 2, since that looks like it's a 0. And then you would have 1, 5, -4, -16, -8. Okay, and you have to start with the division that way. So let's go ahead and do the synthetic division on that. And let's see if we don't get a remainder of 0 this time. So I'll bring down the 1. 2 times 1's 2. Add the column, that's 7. 2 times 7's 14. Add the column, that's 10. 2 times 10 is 20. Add the column, that's 4. 2 times 4 is 8, so it's 0. Hallelujah. Okay, so we got a 0. Okay, that's what's supposed to happen. Okay, now, when I divide a 4th power, this is actually now a 3rd power. So I have to go through and I have to synthetically divide again. And what you're going to do is you're going to take the result. You don't worry about the remainder, just take the result, because that number right there, 0, is your remainder. So what we'll do is we'll start over again. So we just want to write down 1, 7, 10, 4. Now what is another 0? What I see in the graphing calculator is -1. And it doesn't matter what order you put this in, by the way. You'll still get the same final answer anyway. Okay, so we're going to go ahead and do synthetic division there. It looks like the remainder should be 0 based on the graph. So bring down the 1. Multiply, that's -1. Add the column, that's 6. That's -6. That would be 4. -4, so we got it. Okay, so that means the second 0 is -1. All right. Now notice on the graph I gave you, if you look at this, notice that the other 0 looks like it's at a decimal. So what you have to do is you have to do this. Okay, you got to understand that we've divided twice, so that is an x squared, that's an x, and then that's what we would call a constant term like that. Okay, so what you have to do with this now is you have to solve this equation. So that's a quadratic equation. So what you would have is x squared plus 6x plus 4, like that. Okay, and what we have to do is we're going to set that equal to 0, and we got to solve it. Now that does not factor, so what do I do? Quadratic formula, right? Okay, so we got to do the quadratic formula thing. All right, so let's go ahead and do that. Okay, and I'll write the quadratic formula up here. You don't need to do that. If you got it down like you should have, you can go ahead and just plug that in, and then that'll give us our other two zeros. Okay, so we'd have -6 plus or minus square root of b squared. B is 6, so that's going to be 6 squared. 4ac, a is 1, c is 4, and that's all over 2 times 1 like that. Okay, so we'll just go through this, and then this should give us the other two zeros. So what we'd have is -6 plus or minus 6 to the second is 36. 4 times 4 is 16 over 2. So we have that. And then we end up 36 minus 16 is 20. So we got that, and then we have to reduce this. So I'm glad this turned out the way it is, because a lot of times students don't have any trouble with the quadratic formula unless you have to simplify it at the end. So I want to go over that a little bit. Okay, everybody with me okay so far? Okay, what do you do with square root of 20? Break it up. How do I break it up? 4 times 5, right? 4 has a perfect square, so you got to do that. This is the part of the problem that you got to make sure that you know how to do. So we would say negative 6 plus or minus square root of 4 times square root of 5 all over 2 like that. Okay, then we can split this up. So we would have negative 6 plus minus 2 root 5 over 2. Now what you can do is you can split it up. Both of those numbers divide by 2. Both the 6 and 2 divide. So one way to do this is just kind of, you can do this in your head, but you're doing, whoops, I'm thinking ahead here. So we do negative 6 over 2 plus or minus 2 over 2 root 5, and then that would give you the other two zeros in a simplified form. So that's negative 3, 2's cross out, plus minus root 5. Okay, so that's what we end up getting from the quadratic formula. Okay, so our zeros are going to be this then. So back on this answer blank, we already got 2 and negative 1, and we got those from the graphing calculator. The negative 3 minus root 5 and the negative 3 plus root 5, the graphing calculator isn't going to give that to you. So that's the reason why you have to do that synthetic division to even get down to that point. So that's the idea. Does that make sense to everybody? Okay. So when you're doing a problem like this, use your calculator to get the first zero. If it's a 4th power polynomial, you got to get 2 zeros because you have to divide it twice so that you can turn it into a quadratic equation. And once you get a quadratic equation, you either factor it or you solve by the quadratic formula. Okay, that's going to be the idea. Now, the other thing I want to do on this is put this in the factored form and kind of show you how that goes. So we have these zeros like this, and I'm going to kind of slide this over to the side here. Whoops, that's not what I wanted to do. So on the factored form, we're going to do this, and I'll show you how to write the answer. So when you do a factored form, we have 4 zeros. Okay, so it always goes like this kind of. Okay, when you put in the factored form, you got to plug in those zeros that we have. So the zeros are going to go here, and it's always minus whatever the zeros are. Okay, so let's see. If I go back up to where my zeros were, this is what I had. I had 2, I had negative 1, and then I have, and you have to have this in parentheses, I had negative 3 minus root 5, and then I had negative 3 plus root 5 like that. Now we have to simplify that a little bit like that. So we had 4 zeros, and again, the structure is x minus a number. Okay, now you're going to have minus minus, so you'll have to simplify some of this. So what you would get is x minus 2, x plus 1 is what that would be. Now this would be x plus 3 plus root 5. Okay, then the last one is going to be x plus 3, and then distribute the minus to get minus 5 like that. So that's actually the factored form of that polynomial. That's how you would factor that. And synthetic division is what gets you there, see? Okay? So that problem is when you have a 4th power, there can be quite a bit of work in getting those last 2 zeros. Okay, yeah?
So the highest term determines how many brackets there are. So there's 4 because it's x to the 4th?
Yes.
Okay.
Yeah, now one thing that does happen is sometimes you get the same zero twice. For instance, you might end up with a 4th power where you might have x minus 2 squared and x plus 4 squared. That's still considered to be 4 zeros, even though they repeat. So it is possible that you could have a repeated root on these things. Okay. Yeah, but that's but in general, if you have the highest power is 4, you're going to have 6 zeros. That's the maximum number of zeros you can have, but the roots can repeat. Okay, any questions about what I did? Nothing? Everything okay? All right, okay. So that's kind of the idea, and we're going to do this a lot in this 3.3 here today. On this next page, there's a couple of more things I want to do to kind of wrap this up, and then I'll get started into the 3.3, which is the same thing, except it's got complex numbers in it. Okay, so a couple of basic things. This is a basic thing that you want to know, is a polynomial function can't have more zeros than its degree. That's kind of what you were just thinking about there. So on this one, the degree of this polynomial is 3. So that means the maximum number of real zeros is 3. Now, it doesn't mean that it has 3 real zeros. It does not mean that. It means that's the most it can have. Okay? And if it has real zeros, that means it crosses the x-axis 3 times. So you could do a third-degree polynomial, and if it crosses 3 times, it's got 3 real zeros. If it crosses 1 time, it's got 1 real zero, like that. So this is not how many real zeros it is. It's going to tell you the maximum number. Okay? So the next one, real simple. It's a 4th degree, so the maximum number of real zeros is 4. What that will mean is if it has 4 real zeros, it will cross the x-axis 4 times. Okay, or it could even touch, one of them where you have a repeated root like we've talked about. The next one, okay, it could have 100 zeros, all right? And typically, a lot of times on these kind of things are complex. Like this thing right here would have a bunch of complex number zeros also. So that's the idea. You can't have more zeros than your degree. That's impossible. Okay, that's the idea there. Okay, now I'm going to talk about the thing with bounds. The bounds thing, in the world of technology and stuff, this is something that's kind of helpful if you didn't have technology to kind of narrow down that P over Q list for you. So I'm just going to run through the example they have in the book on this and sort of show you how to do this. And this table that I took out of the book, I think will show you what this bounds theorem says. So let's go ahead and let's do the P over Q list on this polynomial. I'm going to do that one more time, okay? And this is what you gotta do on this. Okay, so P is going to be the constant term, okay? So what are the factors of 6? 1 and 6, 2 and 3, right? So if you're doing the P list, you want to write down all of the numbers that go into 6. So you'd have 1, 2, and then you'd have 3, and then you would have 6. Okay, so that is your P list like that. Okay, Q is the leading coefficient. So the factors of 2 are what? 1 and 2. Okay, so what you'd have this time is plus minus 1, plus minus 2 like this. Now when you do the P over Q list, you're going to mostly do this in your head. Okay, so what we would do on this is I'm just going to kind of do this at the side to show you what I'm doing in my head. So I just go 1 over 1, 1 over 2, like that. So I'm just taking the 1 over the 2 Q's, and I do 2 over 1, and then I do 2 over 2. And I do the same thing with 3. 3 over 1, and then 3 over 2. And I do the same thing with 6. I do 6 over 1, and 6 over 2. Now some of those numbers are going to repeat. So and you want to simplify that. So again, all I'm doing is this. 1 over 1, 1 over 2, 2 over 1, 2 over 2, and so forth. Everybody see what I'm talking about there? Okay. So now what we're going to do is just simplify these. So it looks like we have plus minus 1. We have half. So we have plus minus 1 half. That's a potential rational 0. We have 2. Now 2 over 2 is 1, so I've already done that. Don't need to do it again. Then I have 3. So I'll have plus minus 3. I have 3 halves, so that's going to be plus minus 3 over 2. Then I have 6 over 1, which is 6. And then notice that 6 over 2 is 3, and I've already used that anyway. So that would be your potential rational numbers that could be real zeros of your polynomial. Okay? So what I'm going to do is show you what a bound is. So what we can do with this P over Q list is a lot of times you can narrow it down, like the biggest number, the smallest number. The zeros may fall between two numbers like that. So what I'm going to show you basically is this last row. Okay, now just to save a bunch of time, I just took this same diagram out of the book. What they've done is they've synthetically divided like 1, -1, -2, -3, -6, like that. Okay, so they've done that, and then they did the synthetic division on that then. All right, so what I want to show you on this is what happens on this. They even did a -7 just because of what happened here. So here's what happens on the upper bound. The upper bound is if you synthetically divide, I want you to notice that every number in here is positive. Okay, so since every number in that result, that's the result of synthetic division, since they're all non-negative, that would be an upper bound. Okay, so if you divide one of those from the P over Q list, and you end up with nothing but positive numbers, that means it's an upper bound. Okay, so you're not going to have anything past 1, and that's the reason the textbook didn't take any time to divide by 2, 3, 3/2, and 6, because they're all bigger than 1. Does that make sense? Okay, so that's as big as it's going to be. If you see that division there, then you don't need to go beyond that. Okay, the lower bound goes like this. The signs alternate. So if you went through and did these divisions here, if you did -7, which is not a part of this list, but we just decided to take one lower than -6, the signs alternate. So we go plus, minus, plus, minus, like that. So if the signs alternate, like this with sign changes, then it's a lower bound, like that. Okay, that's how that goes. Now, I think on homework, I just gave you a couple of these problems. I'm not going to probably test over this or anything. It's just something that I want you to see. Okay, so the idea is if you synthetically divide and it's all positives, then it's an upper bound. If you synthetically divide and the signs alternate, then it's a lower bound. All right, so that means that if you graphed this on your calculator, what you would find is the zeros would fall between -7 and 1. Okay, that's the idea. So it's kind of useful to do that in some ways, but with our usage of our graphing calculator, we're mostly going to use our calculator to find a zero anyway. So it's not as important as I think, as it would be if you didn't have technology. That's the idea. Okay? Right? Does that make sense, what I did? Okay. Okay, so let me go ahead.